theorem, we have that x is greater than 0. Then we can add the same thing to both sides and preserve the inequality. So we had this, so if we add the same thing to both sides, we preserve the inequality. Then the inverse rule, minus x plus x is 0, is greater than minus x plus 0. And then the identity, that's just minus x. So 0 is greater than minus x. So minus x is less than 0, which is what we wanted to prove. If we start with that x is greater than 0, then minus x has to be less than 0. And I want to say something here. I've mentioned this before. When you're reading a math book, the single reason that you get lost is that the author skips steps, says things in one paragraph, and just assumes that you see why everything's true without spelling out the steps. And so what could take 2 minutes to understand takes 30 minutes to understand because you have to fill in the steps that he or she did not. I think that's one of the biggest barriers to understanding math. So I like when I'm proving these things to spell it out step by step. So there's nothing left to there's no leaps in logic here. We're doing everything step by step. And so for me, at least, that helps you to see what's true. Rudin makes it much more simple because he doesn't, he skips this step because this step is obvious, but still it's helpful to say that's the identity. And the other thing that it does is what we're dealing with is all very familiar here because this is the numbers that we grew up with. As a consequence of that, if you start assuming things, if you start just jumping to conclusions like, yeah, minus x plus 0 is minus x. We all know that that's true, but is it actually true? It's really helpful to actually make yourself identify what rule you're following step by step so that you are sure that you're not jumping to conclusions and making assumptions that might not actually be true in the specific situation that you're in. This also happens all the time. If you know the history of Wiles' proof of Fermat's last theorem, what gets you into trouble is jumping to conclusions. You hand wave and say, well, we all know this is true. But you're just sort of doing it in the back of your head without making it explicit. Then it turns out you're wrong, and he ended up being wrong with his proof. He had to go get someone to help him. And in the end, he didn't get the final proof with just his name on it because he needed someone else to help him. So making yourself be explicit step by step is a good practice, first of all. And also, since we're just getting started, it really helps to hammer home exactly what we're doing. Because it's easy to go through these steps very quickly, but it's helpful to make yourself identify this is the first property of ordered fields. This is the inverse property. This is the identity property. And if 0 is greater than minus x, then minus x is less than 0. So we've shown that if x is greater than 0, minus x is less than 0. Okay. So I think this is useful to be careful as we're going through these. And all of these properties we're going to be using repeatedly when we construct the real numbers and then prove their uniqueness. So to go the other way, we proved that if x is greater than 0, minus x is less than 0, so we have to prove vice versa. So if we start with x is less than 0, then it's the same thing. We can add minus x to both sides. Minus x plus x is 0. And then minus x plus 0 is minus x. Therefore, minus x is greater than 0. So if x is less than 0, minus x is greater than 0. So basically, what we've shown is this is another concept from the axioms of fields, because what we're saying here is actually quite interesting, that a number is either greater than the additive identity or it's less than the additive identity. There's no reason to think that number necessarily is in the middle of the numbers. It doesn't have to be, but it is. So if one number is greater than the identity, then its inverse is going to be on the other side of the identity. So there's an order to them. That's what we've done here with ordered fields. That wasn't the case before we added the order to the field. There were a bunch of elements in the field. Each one had an inverse, but we didn't know how they fit together. Adding the order to it gives them this additional structure that is what gives us, the number line, 1, 2, 3, -1, -2, with 0 in the middle. That wasn't true before we added an order to the field. So it's very interesting. Okay, moving on. I'm going to take this one off again so we can refer to it. So B. If x is greater than 0, reading the wrong one. Yeah, if x is greater than 0 and y is less than z, then xy is less than xz. Okay. So we'll start with, I'm going to switch this around, that z is greater than y. Then we can subtract y from both sides. So again, this is axiom 1 of an ordered field. You can add the same thing to both sides. It preserves the inequality. Therefore, z minus y is greater than 0. So y minus y is 0. That's just the inverse property. And this is an interesting point here, that if one number is bigger than another number, then if you subtract the smaller from the bigger, the difference is going to be bigger than 0. That's obvious. That's also important, and that's going to come up when we're proving the uniqueness of the real numbers. Then, okay, so we were given that x is greater than 0. So therefore, x times z minus y is greater than 0. This is is axiom 2 of ordered field. This is the one that says if two numbers are greater than 0, then their product is also greater than 0, right? We were given that x is greater than 0. We just proved that z minus y is greater than 0. So if you multiply them together, they're both going to be, that product is going to be greater than 0 too. Therefore, my handwriting's gotten messy. So if we start with xz, we can add 0 to that. That's just the identity. And then we can rewrite that. Oh, it's minus first. xz minus xy plus xy. So we had 0. We know from the inverse that x minus xy plus xy equals 0. So we just substitute it in. Now we're going to use the distributive property to take the x out of here. So if xz minus xy, use the distributive property to factor out the x. So we have x times z minus y plus xy. So now we have a inequality. This, what I just did here is axiom 1, because we know, we just showed that x times z minus y is greater than 0. So we know this is greater than 0. So forget about the x plus y. This is greater than 0. We know from axiom 1 of ordered fields that if you add the same thing to both sides of an inequality, it preserves the inequality. So we already knew that x times z minus y is greater than 0. Therefore, x times z minus y plus x plus y is greater than 0 plus x plus y. And then we know that 0 plus xy is just xy. That's just the identity. So what did we end up with here? We have that xz is greater than xy. So we can rearrange that. And that's what we wanted to show. Starting with x is greater than 0 and y is less than z, we've shown that xy is less than xz. So in other words, if x is positive, you multiply both sides by x and it preserves the inequality. So we just showed that. Good. Now, C. C states the opposite. That if x is negative and you multiply both sides of an inequality, it switches the inequality. So if y is less than z, then xy is going to be greater than xc if x is less than 0. Okay. So we still have in both of them, we haven't changed this, that y is less than z. So we just showed in the previous part that if y is less than z, then z minus y is greater than 0, right? We just showed that in the last part. We also know that minus x is greater than 0. We know that because it's given to us that x is less than 0. And remember, part A said that if x is less than 0, then minus x is going to be greater than 0. So if x is negative, then minus x has to be positive. So we know these two things. So therefore, we can put them together, minus x times z minus y. So again, positive, positive. So from axiom B, or from axiom 2, we have that this is greater than 0. Okay. Now, taking this, we have that minus x, z minus y equals minus So we proved this in the last video. I will link to it there. Let me see if I can. That was this one. If you have minus x times y, that's the same as minus x times y. That's all we did here. We had minus x times y is minus the whole thing, okay? Therefore, so we started with minus x times z minus y is greater than 0. This equals this. So if this is greater than 0, then if we take away the minus sign, we have that x times z minus y is less than 0, right? We started with this. We showed that this is greater than 0, and this equals this. It's the same thing. And from part A, if this thing is greater than 0, then if you change the sign, it's going to be less than 0. Okay, now distribute the x through. So we have xz minus xy is less than 0. Now we can xz minus xy plus xy is less than 0 plus xy. So we just used axiom 1 again. We had an inequality, added the same thing to both sides. These are 0, so xz minus 0, that's just the inverse, is less than 0 plus xy. So if you subtract 0, that's the same as adding 0. I guess I could have actually, I don't know why I made that minus. So that's xz is less than xy. And that was exactly what we wanted to prove, that xy is greater than xz. So we started with x being less than 0, y being less than z. And we proved that if x is less than 0, then it's going to switch the sign. And we have xy is greater than xz. Okay. Okay, now D says that whenever you square something, all squares are positive, which, by the way, is going to lead to complex numbers, right? Because we immediately get another problem. What if the problem says that x squared equals minus 1? We just said that if for an ordered field, x squared can't be minus 1. So that this actually, never mind what I said earlier about that it's just hard to put an order on it. You literally can't. If it's an ordered field, then x squared is going to have to be greater than minus 1. So we would have to add, that's why we have to add I to it in order to even make it possible. But by doing that, it's no longer an ordered field. This proves that. So if x does not equal 0, then x squared is greater than 0. In particular, one is greater than 0. Okay. So we're going to look at this when x is greater than 0 and when x is less than 0. If x is greater than 0, then we've already done it because axiom 2 says that if you have two numbers that are positive, then the product is greater than 0. So, right, if we multiply one number that's greater than 0 by another number that's greater than 0, the product is greater than 0. So positive numbers have already been done. If x is less than 0, then we have that minus x is greater than 0. That is the first thing we proved, that if a number is less than 0, then its opposite is greater than 0. Therefore, now this is what we just showed, right? If this is greater than 0, then if you square it, minus x times minus x is going to be greater than 0. That's axiom 2 again, same as up here. Now, we learned before minus x times minus y equals x times y. So we have from that part that minus x times minus x equals x times x, which equals, of course, x squared. So we just showed that minus x times minus x is greater than 0, and we know already that minus x times minus x equals x squared. Therefore, minus x squared is also greater than 0. Finally, the last thing we're showing is that 1 is also greater than 0, which is clear now because since 1 equals 1 squared, then we know that 1 has to be greater than 0. Because we know that 1 squared is greater than 0. We know that 1 squared is greater than 0, and 1 squared equals 1. So 1 is greater than 0 too. Okay, one more. Finally, this most interesting one, that if 0 is less than x is less than y, then 0 is less than 1 over y is less than 1 over x. So really what we're going to do here, there's really 3 different inequalities in here, and we have to prove all 3 of them to make this, to show this is true. So one is that if 0 is less than y, it implies that 0 is less than 1 over y. In other words, it's kind of the opposite of addition inverses, that inverses maintain their sign, that if a number is greater than 0, then its inverse, its multiplicative inverse is also greater than 0. Then we have to show the same thing is true for x, which obviously if it's true for one, it'll be true for the other. And 3, finally, that if x is less than y, that implies that 1 over y is less than 1 over x. Okay, so we actually need to show, first of all, that we're not just showing that if x is less than y, then 1 over y is less than 1 over x. We're also showing that they maintain their sign. Okay, so 1. So we know that if y is greater than 0 and some number v is less than or equal to 0, then yv is less than or equal to 0. Now we know this for two reasons. The less than, this is one of those things, it's obvious, but just to show why. So if y is greater than 0 and v is less than 0, then from part C, if we multiply both sides by v, we have to change the sign. But of course that just equals 0, so we have that yv is less than 0. But then of course if v equals 0, then of course yv is also going to equal 0, so then 0 equals 0. But y times 1 over y equals 1, right? This is just the inverse property, the multiplicative inverse. Y times 1 over y equals 1, which we just showed is greater than 0. So y times 1 over y is greater than 0. So if we plug in 1 over y for v, then we would have that v is greater than 0. But now using the contrapositive, if we're starting with y is greater than 0, but we have that yv is greater than 0, then we've proven the opposite of the conclusion here. So one of the assumptions here must be wrong. Therefore, v must be greater than 0. Because it can't be, because we proved that this isn't true. It's the opposite. So then the assumptions here must be wrong. We're given that y is greater than 0, so v must be greater than 0. So if v is greater than 0, therefore 1 over y is greater than 0. Okay. Okay. So the same thing works for x, obviously, because it's just the same thing. If x is greater than 0, then 1 over x is greater than 0. So the last thing we have to show is 3, that if x is less than y, then 1 over y is less than 1 over x. So we've just shown that 1 over y and 1 over x are both greater than 0. So we have that 1 over x times 1 over y is greater than 0, because a positive times a positive is greater than 0. So taking this, we're just going to go through a few steps. So we're given that x is less than y. So that implies, so if we multiply both sides of this by this product, then we'll see what falls out. So we have x times 1 over x times 1 over y is less than y times 1 over x times 1 over y. This is just axiom 2 again. If you have an inequality, then multiplying the same thing on both sides when it's greater than preserves the inequality, right? So we showed that this is greater than 0, so if we multiply something greater than 0 by both sides, it maintains the inequality. So then x times 1 over x is just 1, so that leaves us with 1 over y. And here, the fields are commutative, so we can switch these, and y times 1 over y is 1, so we're left with 1 over x. And that's what we wanted to show. So if x is less than y, it implies that 1 over y is less than 1 over x. Okay, so those are the properties of ordered fields. We'll be using all of these repeatedly, and that's it for our the general concepts of field, least upper bound property, and ordered field. Now starting now we're going to show that there exists a ordered field with the least upper bound property, and then we'll show that it's unique.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.